Hi, physics friends. So today we're going to be talking a little bit more about electric circuits and about that current and the relationship between electric current, the voltage that comes from usually our battery or our power supply, and our resistance that's in that circuit. So you should have already done the Ohm's Law kind of inquiry interactive, and I want to talk about that for a minute. So how did the current change when you increased the voltage? So increasing voltage should have produced more current through the circuit. And then how did it change when you increased resistance? Well, increasing resistance should have slowed the current down. You should have had less current through your circuit with a high resistance. So we actually have an equation that relates voltage, current, and resistance, and we call that Ohm's Law. So Ohm's Law is the formula V equals I times R, where V is the voltage across any resistor, I is the current through that resistor, and then R is the resistance value of the resistor. So we can use this formula. We'll look at it today in like simple circuits with single resistors, and then we'll get into how this can get more complex when we look at a whole circuit with multiple resistors, because you can also apply this to the whole circuit if you know more about the resistance within that whole circuit. So let's look at a sample problem, just a simple one. So we want to know the current through a 333 ohm resistor if the voltage across that resistor is observed to be 1.5 volts. So we know our formula is V equals I times R, but in this case we want to find I, current. So if we rearrange that formula, I equals V divided by R. So looking at our givens in this formula, our voltage is 1.5 volts. V is 1.5. Ooh, excuse my sloppy handwriting on here. And then our resistance is this 333 ohms. Ohms are that little horseshoe. Ohms are the measurement for resistance. So 333 right here. So when I divide that, I actually get a very small number. A lot of circuits that you use in everyday life, like in your computer circuit boards and everything, have very small amounts of current. So I get 0.0045 amperes. We can also look at that and say, well, that's 4.5 milliamps, 4.5 thousandths of an ampere. Okay, so if we're looking at a different situation, let's say that we have something that you've attached a little mini light bulb to a D-cell battery. So a D-cell battery has 1.5 volts. So this would be the negative end, that short side, the positive end, the long side, and we're connecting them to some wires. Those wires here are connected to a little light bulb. So there's my light bulb. And that light bulb has a resistance of 4 ohms. So I've drawn my circuit. The conventional current, the flow of positive charge, is actually going from the positive, well, we don't remember positive charge doesn't flow, but the theoretical flow of positive charge, the conventional current, goes away from the positive terminal of the battery through the light bulb and back to the negative. And if we want to find how much current there is, then we're just using that formula again. So on the last slide, we rearranged it. I equals V divided by R. That's just another form of the same equation. And we still have this 1.5 volts for our battery. And in this case, we only have 4 ohms of resistance. So in this type of circuit, we have 0.375, running out of room there, amperes of current. So that's a little bit more. So most of the time with current, you're going to get pretty small numbers. You're going to see some decimals there. And that's we don't really want large amounts of current flowing through things. The only time we would want that to happen, like when we have large amounts of current also, that usually creates a lot of heat. So heating devices usually have a lot of current flowing, like more current flowing through them. but we want to be very careful with electric current because that's what can be dangerous for us and for our bodies. So let's talk about how we can control current. Let's say we have that, like we have that circuit, and we have that battery, we have that light bulb, we need a certain amount of current to flow. Let's say that's too much current. Or maybe we need to hook up another device that has the same amount that uses the same amount of current, but we want to use the same power supply. So we have different ways that we can connect our circuit components to control our current flow. So those two ways of connecting components of circuits, you can say that components are either in series or parallel. So in series, so the diagrams on the left, our components are put together so that the current flows separately through each, or sorry, not separately, it flows like consecutively through each device. So we have our circuit, we have our battery, the current travels from the battery, and in order to get back to the other end of that battery, of that cell, it's got to go through one light bulb and then through the other light bulb. So that's what the electrons have to do. They're being pulled around this circuit simultaneously, going through both, but they have to make it through both. If you disconnected one of those bulbs, then you would break the path and that current can't flow anymore. Parallel components are different though. They have separate loops. They each have separate paths to the battery. So if you look at the diagrams on the right, these parallel components have junctions, places where wires meet. So in that light bulb that's closest to our battery, our cell there are places where these wires connect to each other and to the bulb in the middle. So that current can come from the battery, and some of it can travel through that bulb closest to the battery, or the rest of it can keep going and go out through the next bulb. There would definitely be, if you can see, let's see, these junctions where these wires meet, that tells you that you have a parallel, you have circuits or components of your circuit in parallel because there is a junction there. So these are junctions. So that current does split up, so each component, each light bulb in this case, only gets a fraction of that current, of that electric current. Where in series, like all the current has to flow through both of them. So if we look more at these components in series, that current's the same everywhere. So the current across each resistor, or current traveling through each resistor, is going to be the same. And then the voltages actually add up to the total voltage across that whole circuit, the total voltage of our battery. But in parallel, those different branches, they are each connected separately to the battery in this case. So each bulb that's in parallel has the same voltage across it as all the other bulbs in parallel with each other. So they all receive that voltage difference, remember that charge difference of 12 volts. But you have a current that's split up in this case. The current would have to add together to become that total. Also, when the current is flowing around this circuit, it would split off to each bulb, but these wires that are connected to the battery are going to carry all the current that goes through each bulb all added together. So those connecting wires have the most current flow. They would have that total current flow. So in your house, we have parallel circuits, and you actually have circuit breakers that control groups of parallel circuits, like usually in each room, or maybe a few for your kitchen, some for specific appliances. Like your air conditioner is usually on its own parallel circuit with its own circuit with its own circuit breaker. But in your house, you've got switches that will control each of these different parallel loops of circuits. But let's look at a simple example and see if we can figure out which one this is. So is this one series or parallel? Pause the video if you need more time to think about it. right? But it is parallel, so each bulb has its own path to the battery terminal, and we can see that if one like burns out or breaks, then the other one still stays lit because it still has its own path. All right, what about this one? Okay, so this one's also parallel. We have these junctions here, where these wires connect to each other, but split off through each light bulb. Those tell us that it's a parallel circuit. So even if one bulb goes out, the other one still has its own path back to the battery. Now this one, take a second if you need to, pause the video. This one is series. So this circuit, the current, if it can't go through this first bulb, there's no way for it to travel through the second bulb. If the second bulb weren't lit, there is no way to pull the current around back to the battery. So these are in series, they're in the same loop of wire here. All right, so what about these two? One of them's series, one of them's parallel. All right, so the circuit on the left is series, they're all in the same loop, while the circuit on the right has junctions where these wires meet and split apart and then meet again. So that would be parallel. Take a second for this one. And this one's also parallel. So this one, it's kind of tricky to see, but the current can go through this R1 bulb and go through this path and meet back up to the rest of the circuit, or it can continue through this red wire on the top and go through the other bulb before meeting back. Oh, goodness, sorry. Cat's tapping my watch. All right, so this one is actually really tricky. So this one, we have some bulbs that are in series, and then these motors here are in parallel with each other. But the motors are actually together. This parallel piece with the motors is actually in series with the bulbs in the rest of the circuit because they are continuing in this path that completes one loop of the circuit, but individually these motors are in parallel. So you can have combinations where you have some components in series and some components in parallel. In fact, you'll see that a lot, especially when we have a switch that's controlling something, because a switch would be in series with whatever it's controlling. So this is kind of the same way. We've got resistors in parallel, and then two more resistors in parallel, but then this parallel piece is in series with this other parallel piece. Okay, so how does that exactly control the current? We do have some equations, some formulas that we can use to describe what's going to happen with resistors in series and in parallel. In series, we add up all these resistances. So the total resistance, when you put resistors in series, the total resistance is going to increase. We call that equivalent resistance, the combination, what is the total resistance of a combination of resistors. But in parallel, we're actually adding the inverses to figure out the inverse of the equivalent resistance. So when we add more resistors in parallel, each resistor is going to stay the same, but overall our resistance decreases for the circuit. So what I want you to experiment with next, you're going to go to the Electric Dollhouse Interactive, and follow read a little bit, then follow the lesson there, and play around with that dollhouse and see if you can apply some of this to a simulation of an electric dollhouse. Okay, so I hope you learned a little bit from this video, and have a great day exploring electricity.